Okay. All right. So, what have I done, and why is it important to you? Currently, what I've been working on is a sand printer. Now, you might be wondering why one would want to print sand, and in short, it would be there's a lot of stuff I want to make that's more complex than this core right here. It's a water jacket, right? There are some features on this water jacket, like these holes, that I only want to be on this part of the mold. There's a lot of other ways I'd like to redesign this for manufacturing. 3D printing, that sort of core, or anything more complex than that, you don't need as many design revisions to make it moldable. All you need is something that is castable and has directional solidification. So, the printer itself, what I worked on is essentially making an SLS machine. There are thermosetting binders that are pre-coated to sand, specifically for shell molding. So there's commercial sand available. Technically, any SLS machine you could throw this sand into and make cores for your foundry at home. Only problem, none of them are really quite big enough for your at-home cores. What I worked on was figuring out the settings for this laser to sinter sand. Technically, from an engineering perspective, what's happening is the laser itself is pushing heat into the resin binder, which then cures the binder in a specific pattern to hold the sand grains together. So, what I found out for settings, you can see some of the videos that are going right now. I was using a 100-watt fiber laser into a galvanometer, which is a bunch of mirrors that essentially move the laser beam around in a measurable path, which then those laser beams go and sinter sand. From there, the fiber laser requires two main settings, frequency and power. And speed, but the speed is controlled by the galvanometer. The frequency and power is controlled by the laser. That's useful for later. The settings based off that is I needed 50% power from a 100-watt laser, so I needed 50 watts of power at a frequency of 60 kilohertz to move at 100 millimeters a second. I was able to, maxing out the frequency, get the printer to go about 150 millimeters a second. When I'm referring to a printer here, I'm referring to like the fixture that I printed plus the manual setup that essentially acts like a printer itself. So, getting back to the main topic, the three main settings that I worked with were frequency, power, and speed. Now, technically, there's other settings with like Q pulse and all this other stuff. But that's not important. The bottleneck, limited by frequency, I was able to get up to about 150 millimeters a second, but that was with maxing out the frequency at 80 kilohertz. Still the same amount of power. Now, the thing that really blew my mind, if you're limited by frequency, the maximum frequency you could get is an infinite frequency. It's like always on. Fun fact, those lasers exist. So what I'm going forward be working with is going to like a CO2 or a diode laser fixed on a gantry system. Technically the CO2 laser and diode laser could go into a galvanometer, but for $500 I can get a gantry system. For $25,000 I could get one of those little galvanometers. Personally, I'd rather go with the $500 option because I'm already at this max speed I've gotten so far is 100 millimeters a second. The most I'm expecting with a constant beam is like 1,000 millimeters a second. And those gantry systems can still maintain their operation without really being limited by inertia up to that speed. So, the next steps that I'm going to be working on is essentially a control system and mounting the CO2 laser to the bigger aluminum fixture, which I have on screen, hopping up over here. That's about it. From there, I'm going to run more settings, see if I can essentially get the printer to run faster, and what other settings would be affected. Because power and speed are the main two with a CO2 laser. That's covering what I did, kind of covered why it's important, and my next steps. So you could go and buy a binder jet printer from like EX1 or voxeljet, but you need $1 million. These printers too also are kind of overkill. Like size wise, so big molds are important, but for my size of castings, I don't need something that covers up a whole room. I need like a desktop machine. This is also feedback that I've gotten from some of my friends, is that, hey, make it small. Like, if you make this for like $5,000 and it's a desktop machine, people would buy it. Not even just cheaper, but also I got feedback from bigger companies, and they were like, well, lasers themselves can move faster than a thing with actual inertia. So if you get the right settings, you can speed this thing up quite a bit, presumably, because it's a laser. That's also part of the next steps, is that this thing, with lasers, you can go faster. You don't need $1 million piece of equipment. It's achievable. And that's about the short story that I have for you guys currently. I wanted to get some of this information out because I think it's exciting. I also haven't posted a video in a while, so got some big projects in the work for myself as well as the machine behind me. That's kind of an update. If you look into sand printing, you could make cores more complex than this with way less effort, way less post-processing. All you're paying for once you get the machine is the filler material. The biggest thing is just, this is really straightforward technology, and I have some pretty useful stuff coming down the pipeline that you guys might be interested to see. So that's what I did. What I did was figure out settings to selectively sinter sand and then also fuse layers together. It allowed, the sand itself remained at that like ideal yellow color without getting brown or burnt. You can see whenever you look at like core machines, if they run too hot, the outer shell itself gets like a very, very dark brown. Besides the point, that's what I did, is I worked on settings, figured out settings for a fiber laser feeding into a galvanometer, which then distributes the heat at about 100 millimeters a second. Power going up really didn't do much. It kind of hurt the process. Found out with higher frequency you can get away with less power, but that's kind of, you can see all the results and stuff that I took here. If you want actual results, email me or like send a comment. I can share the data with you.